we started talking about existence of solutions, and we talked about this notion of adding conjectures. Now remember, I just want to emphasize, when you add conjectures, you're solving a different problem. You have a way to relate it to the original problem, in that an equilibrium of the original problem is an equilibrium of this new conjectured problem. However, an equilibrium of the new problem need not be an equilibrium of the original problem, and that's in some sense a shortcoming. But our hope is, and this is, we still don't have a clear understanding of this. The question is that in some of these cases, is there a modeling enhancement or a modeling resolution that can help make these problems what I call better posed, right? So, but we haven't made that precise yet, so I don't want to kind of. So the rest of the time, what I want to do is talk to you a little more about going back to the original game, the multi-leader, multi-follower game, and asking the simple question. Well, not as simple, it was a painful question. Can you actually, under what conditions can you actually show an equilibrium exists without making strong assumptions on the lower level problem? So if you look at the work by Shirali, Su, and others, what they've done is they've said, well, if the follower level problem has a solution that is unique, and I can eliminate it, and I have a structure in the solution set, I can do a little more. Now, for an optimizer, that's not particularly desirable, because that starts putting very stringent assumptions on the lower level problem. I don't like doing that. I'd rather come up with settings which are less, what should I say, for which I don't have as strong a condition, but I don't have as strong assumptions. Okay. So let's consider the multi-leader, multi-follower game eScript, which was the original one. So in this game, what we have is, remember, we want phi of xi yi x minus I to be less than phi ui vi x minus I, right? So this is the standard approach of the Nash requirement, while meeting the equilibrium constraints, right? So this one's low. So now I should also note that sometimes people have been interested. So there's work by Danny Ralph and Shimin Hu, where they've looked at a local Nash. So sometimes if you write down the KKT conditions of each MPEG, the strong stationary conditions, and then if you can get a joint solution to all of them, you get what is called a local Nash. Okay. So economists don't quite like this, but sometimes that's the best we can do. Okay. So the complementarity researchers like Todd Munson, Michael Ferris have tried to push this direction, because in some sense, from a computational standpoint, that's often the one that we can have access to. So if you're looking to solve these problems, that's often a good way to do it. Write down the stationary conditions and then solve them just as you would solve the complementarity conditions of a Nash game. Okay. So now let's look at a particular subclass of Nash games called quasi-potential Nash games, well, multi-leader games. So before I do that, I want to give you a quick tour of something called potential games. How many of you have heard of potential games? Okay, a few of you have heard of potential games, right? So let's go through potential games, because this is something that we use next. I didn't talk about potential games, but it's an avenue that has some similarity with the integrability approach, which allows you to construct an optimization problem. So consider a function, consider a game, minimize fi of xi, x minus I, and it's a pure Nash game, okay? So a game, G script, is called a potential game if there exists a potential function pi of x such that for all I, pi of xi x minus I minus pi of yi x minus I is equal to fi of xi x minus I minus fi of yi x minus I. So the difference in the potential function, keeping all the rival decisions fixed, is equal to the difference in the payoff of that agent, that player. How does this help you? Well, it helps you because the minimizers of this function, pi of x, where x lies in the Cartesian product of x, provide you with a Nash equilibrium. Okay? So you can reduce the problem of computing a Nash equilibrium to getting a solution to an optimization problem. Now, several issues that emerge when you do this. The first is that in some cases a potential function emerges naturally, so you know what it is. Right? So for instance, if I told you that fi of xi x minus I is, well, in the case where actually that's not a good, but if I told you this is the case, right, then you can construct a potential function quite easily. Right? There's just a joint like Cournot. Okay? So there are, Cournot in fact has, Cournot games have a potential, are potential games, but the potential function is not that easy to articulate. It's a little nastier than you think. So in general, getting the potential function is not that easy, and even if you did get the potential function, it's not necessarily jointly convex in all of x. Okay? So you'll get nonlinearity across these, and so that problem is non-convex. So then computing this is, getting a global minimum of this is not always that easy. But the point that I want to emphasize now is that can you do this for multi-leader, multi-follower games? Because we know for multi-leader, multi-follower games, if I can use this as an existence vehicle, we do know that for this problem, if pi of x is a continuous function and the Cartesian product of xi is a closed, convex, compact, if it's just a bounded set and it's closed, we know that pi of x achieves the minimum if it's compact, right? Just from Weierstrass's theorem, continuous functions achieve a minimum on this set. If you have coercivity, you can also get that. And if you get a minimum, then you've got a Nash equilibrium. So the potential game provides you with a vehicle to claim existence. The question is, can we do something similar in the case of multi-leader, multi-follower games? And if so, under what conditions?
Just to make sure that I got correctly. So this equilibrium and that optimization problem, they are not necessarily equivalent.
No, they're not. It's not like the KKT conditions don't match. There's nothing.
Yeah, okay, good.
Yeah.
And if our original pure Nash game has multiple solutions, are they all also the solutions of the optimization problem?
So it goes in the other direction. If you get solutions of this, you get equilibria of that. Okay, right? So I'm not sure if I can trace every solution back to this.
But every solution of this is
as an equilibrium of that.
And how to achieve it?
So you have to get a global minimum of that.
No, how to construct it.
So the potential function, so if you go back to the paper by Mondrer and Shapley, they have some discussion on generating these potential functions. In some cases, it's quite obvious. I'll show you some. But the original paper actually has some discussions on that. Okay, so Shapley is Lloyd Shapley, who worked on cooperative games, so he got the Nobel for cooperative games. Okay, so let's consider the case where each tuple of leader decision there's a unique follower equilibrium. Okay, let's just look at that case. In that case, what we have is I can get rid of y of the equilibrium constraint, and I can make this into pure Nash. Right? I can always do this. In fact, if I can look at the follower level problem and regularize it, it always has a unique solution, and I can write this in some abstract form, S of x. Okay? Now, because it's unique, if you have two players, we cannot disagree on the choice of S of x. Everybody has to have the same given x, right? Now, you can come up with what is called an implicit potential multi-leader, multi-follower game. So an implicit potential multi-leader, multi-follower game, the ith leader solves this, and there exists a function such that for all x prime this holds. So now the question is that does a potential function hold? If such a, right, so if you have such a potential, if you have this potential function, then any global minimizer of pi is a global Nash equilibrium of. Okay? So now the question is, when is it that this holds? When is it that you can get this? So that really is model centric. You'll have to figure out, you'll have to see your model and then check it. For instance, if you have a high degree of nonlinearity that comes from x, it may not be that easy. but that's something worth checking. But this is an avenue, okay? In principle, the above is an existence result. If I can show, so because this can be easily guaranteed. If I give you an optimization problem with where I have to minimize pi over the set x, and if x is, now remember, x is not, does not contain equilibrium constraints. Xi could be closed and convex. So capital X is the Cartesian product of closed and convex sets. If they're bounded and pi is continuous, you immediately have existence. Okay, under very mild conditions, you can get existence if such a implicit potential function exists. Now, the problem is that, of course, ascertaining the potentiality of this implicit game is difficult, since it requires an expression of a closed form expression of S. Now, for instance, in the game that I just showed you, the one that I just showed you where I had y was the max of something. Now, in that case, you might be able to do something. But in general, if you have a very nasty expression, even if I told you that I regularized the complementarity problem and I tell you it's single valued, you still don't have access to the algebraic structure. If you don't have access to the algebraic structure, how are you going to prove its potential? It's not that easy, right? So I want to warn you that this approach is not that easy. This approach is not that easy because S of x complicates the problem, and for you to even ascertain potentiality is difficult. This suggests to us that it's not a good idea to eliminate S of x. Okay? So the question is that suppose you do not eliminate S of x. Can you come up with something which is easily verifiable but maybe not as far reaching? Okay, so that's when we came up with something called a quasi-potential multi-leader multi-follower game. So in this case, there exist functions phi1x to phi nx and a function h of x comma yi, such that for each player's objective is given by phi I of x. So the player's objective is entirely in terms of leader level decisions plus the interaction with only its own follower level decision. So you need this structure. So if you have an epoch and you have this structure, okay, then there exists a function, and there exists a function such that this has a potential function. This is what I described about the potential function. Then the function pi plus h is called a quasi-potential function. Okay, so h is a common function that all players share, right? So this could be like a price function or something of that sort. And this is a leader level function. So when you compete with your, so imagine you play Cournot in period 1 in leader level decisions. Then this is the potential function that corresponds to the leader level decisions. Notice that the function h does not have a subscript I and is thereby the same for all leaders. Essentially, a quasi-potential game has objective functions that can be written as a sum of an x part and an x comma yi part, right? Where the x part admits a potential function and the x comma yi part is identical for all players, right? Now there exists a potential function. So this was Jalal's question. How do you create potential functions? If you can get a function where the gradients match, right? Because think about it. What is this effectively saying? This is effectively saying that change, if you hold everything else the same, is the same of the change in the gradients of the change in the values of the potential function in the same argument. But that's effectively, if you take limits and divide by this, what do you find? It's the gradient, right? So the gradient of the potential function has to match the gradient of that specific payoff function or cost function for all x and for all I, okay? So if that holds, then the function pi is a potential function. So if I have that, so a potential multi-leader multi-follower game is one where leaders have those objectives, and I can write down a centralized problem such that you have this potential function plus this common function and these complementarity constraints. So I have an MPEC, and so then the question becomes, does the MPEC have a solution? And I've given you existence conditions for that. So through this vehicle, we've been able to come up with a setting where you can actually ascertain the existence in a relatively cheap fashion. But this is not the panacea for all our ills, right? There are lots of issues with going in this direction. The first of the issues is, does your objective function satisfy this structure? Where's it gone? This structure. Not all problems are going to look like this. But we don't think that it's altogether, it's so outlandish, because it says there's a leader level interaction, which could be like players playing a particular game in period 1, and your interaction with the followers is only with a specific follower, with your own follower, not with all the followers, which is also not surprising. Okay? So the proposition is as follows. Consider a quasi-potential multi-leader, multi-follower game. If x of xw is a global minimizer of this problem, then xy is a global equilibrium of E, where yi is equal to w for all I. Okay? And now the question is, how do you get this? So the way, sorry, this one. How do you get this? Well, if f script quasi is a non-empty set and phi is a continuous function, then the minimizer exists if either pi is a coercive function over f quasi, or if f quasi is compact, right? So it's not impossible to get existence if you abide by this structure. Now you'll have to tell me if it works for your applications, but that might help us think about how to modify, extend, change it. Okay. So
something similar to this submodular games in game theory.
so so you can use potentiality there, but these are not those types of games. I mean, so potential games, if I'm not mistaken, submodular, that is an instance of a potential game, but I think that is an instance. Okay, questions? So as I said, this is a nasty class of problems. There are no clean existence results unless you use properties of a model. This appears to be one of the few results that at least I'm aware of, where we have model free, for a generic set of functions you can get existence. Now we are unclear whether this structure, how useful it is for for folks who model in this. So that's why I was curious how many of you actually face EPEX. So you asked about EPEX, so I was curious whether whether your model abides by this.
I've not yet used it, but I might, so
Okay.
just to know.
Okay, try and make sure it looks like that.
How do you get H, by the way?
Just pretend one exists. I'm joking. No, so H in some cases, so H in certain cases H appears naturally. So for instance, if you're looking at communication networks, H is like the congestion in the link. But look at the congestion in the link is common for all players. Now it's different from Cournot, because Cournot, the interaction in terms of the cost function occurs in terms of the revenue function, and that depends on how much I sell. So Cournot is not the best example. You have to come up with some sort of function which is a common function for everybody. So Cournot may not be the best thing. I think instead, I'm not sure. So that revenue function isn't a good one, because what is that revenue function? That revenue function is xi times h. So the thing is that if it's in the first period, it's one thing. The problem is if you look at the second one, what is that from the standpoint of a market? yi could have the real-time decisions, right? Now what you're saying is that the real-time, how do you charge each player? How does each player benefit from the real-time? It only benefits from its own generation facilities. But here I'm saying that everyone gets something from the entire vector of dispatch. That's not true, right? There's something off in that. So this is not a great fit for Cournot, for our markets. I think there are other examples. So we tried to weaken this, but we have not been able to get it to work. We tried to make this hi. We haven't been able to. So this function has to be common, otherwise it doesn't work. Okay, maybe there's some other way, but not this way.
Why can't it be something related to the transmission constraints in power markets?
So but the question is that if it's transmission constraints, why would a firm? So the firm would not So remember, the transmission constraints are there, but the issue is that why would it show up in your objective? So it's hard for us to kind of come up with a setting, bless you, when that works.
But then you said in communication networks.
So in communication networks, what happens is that each player that sends something across the link, the congestion in the link grows based on the aggregate flow through the link. So it grows in this fashion. Suppose we all use a link, then the congestion grows like this: b minus the summation of xi squared. Right? So if whatever we all do, we all face the same congestion cost. It's not a scaled congestion cost. There are problems like this where I pay proportional to the congestion and I scale it based on what I contribute. But if I do an unscaled version, it's exactly like that. Okay. So there are some problems it works for, but there's a lot of problems it doesn't work for. It's not the most general. I mean, we're aware of that. Okay. So now what I wanted to do in the last 10 minutes or so is to talk about revisiting our general framework and seeing how to kind of capture Stackelberg and the multi-leader, multi-follower setting. So the networked energy market model presented in the previous section imposes a key assumption on the nature of the interactions. In fact, in particular, it assumes that the generating firms compete in a Nash-Cournot game while taking transmission prices as a given, right? So in most sophisticated models, generating firms are often modeled as being capable of anticipating the optimal reaction of the system operator and are effectively Stackelberg leaders with respect to the ISO's reaction. Right? So this was seen in the work by Hobbs and Hellman, and a related model was presented by Cardell, Hitt, and Hogan in '97, where the generating firms trade in energy and transmission congestion contracts. And these contracts are priced through a lower level competitive equilibrium problem, resulting in an EPEC. Okay, this was probably the first instance that we know of not the first instance, there were multi-leader, multi-follower games, but this was one of the few instances where they actually tried to solve it. Okay, so here are the equilibrium constraints corresponding to the transmission operator. These are the complementarity constraints. These are the flow balance constraints. Okay, if you have a firm that is strategic with respect to the system operator, then that firm is going to introduce these constraints into his objective. So this is firm I. Firm I optimizes over the entire network. This represents her revenues, her costs, and then the transmission costs. Right? These are the reactions of the ISO. Right? These are the flow requirements. This is the specification of price using the price setter. Okay? These are the equilibrium, and these are just non-negativity and capacity requirements on generation, and these are conservation laws on generation and sales. Okay, so the big difference is this. You're now strategic with respect to the transmission decisions. Okay, so now you can define what is called the hierarchical unified equilibrium, which is given by a multi-leader, multi-follower game, and you have this structure. Generators are Stackelberg leaders with respect to this, where these problems, the ISO's problems, are defined like this, and the flow balancing problem is like this. Now, for this general problem, existence is an open question, right? The existence question that we have addressed is a very narrow question. So this remains open, right? So I think it's still unresolved. There have been lots of people who've written papers about this, but the theoretical question is open. Okay. So if you're looking to get famous immediately, like today, that's the problem. Okay, so I'll stop here, and I want to thank all of you again. I know that along the way I've had to adapt and change, and slides have kind of, but I really enjoyed our interactions. I'm looking forward to seeing all of you at upcoming meetings, and feel free to contact me at any time. If I update the slides further, and I've got some things that I've changed, I'll try and renumber them so they go from not 0, 1, 9, 6, 2. We'll try and get them from 0 to, because I had slides in the middle which I've had to pull out just to kind of adapt it. So that's why you're seeing weird numberings. So I'll try and get them numbered so that I'll just send you the ones that you have, that you have, but I'll clean them up. Okay, so thank you again for everything. It's been good. And so if you have questions, I'm around and we can talk more.
Can you like explain a little more about? You said that maybe forward market and day ahead market or spot market. There could be a stagger between.
Yeah. So exactly here. So instead of, so if you look at, let me give you a quick blurb on that. So there's this well-known paper by Alaz in '92 and Alaz and Via in '93, I think. So in this paper, what happens is that firms compete in the forward market subject to the clearing of a subsequent spot market. Now in their case, they drop inequality constraints. So the spot market equilibrium can be computed in closed form as linear equations. So they're able to actually analyze the equilibrium because now their MPECs are actually just simple linear programs. Right? In fact, with their linear programs where the equilibrium conditions are linear equations. So it's really kind of tractable. So let me tell you what decisions they make. So essentially in period 1, they have a forward decision. And in period 2, they have a spot decision, let's call it GI. Okay. And now the pricing that is done, so they have a no arbitrage assumption on the price. So what happens is that, so if there's a PFI, the expected outcome in the real time is G minus Fi times some P omega. Okay. And then there's some requirement here, F is to be something, I can't remember. And you have that this spot market they have a set of equilibrium conditions which are linear equations. Okay. But now if you look at this, what is interesting to note in this is you get P of Fi minus Fi times expectation of P of omega plus expectation, and this is G of omega, I'm sorry. So you get expectation of some G of omega, P of omega. So this is the expected revenue from the spot market. But if you look at this, once you make an assumption that you have a no arbitrage assumption, it means forward price is equal to expected spot price. So this disappears. So you're just left with this revenue and you have some forward requirements here that relate forward and spot. I can't remember exactly what those are. So now you can see this is a pure Nash game. It's very easy to analyze, and that's what Alaz and VR did. And they were able to kind of comment on the role of how the presence of forward contracts allows you to have less volatility. But I worry about some of these claims because a lot of these claims that are made have been kind of, there have been counter claims that have been made with more elaborate models. Their model is very simplistic. So I know there's this belief that working with very simple models is a good idea in economics, but sometimes what happens is that you come up with these very sweeping claims and those don't work whenever you have constraints. So they work in a very narrow regime. So I'm a little guarded about making claims like, this leads to this, which is in an economic setting when you have extremely complicated situations which are reduced to something very simplistic. Then you cannot make claims in this regime and expect them to hold in the most complex regime. I think you have some intuition, but that shouldn't go beyond that. So in any setting where you have multiple clearings, so here we had day ahead and real time. You could have forward and day ahead. In this particular case, what you had was you had generation was a leader and the system operator was a follower. So actually you have that clearing at the same time, but it's just that you can anticipate their reactions. You also have these problems showing up when you're solving expansion problems. So if firms are deciding to expand in generation, they're leaders with respect to the subsequent clearings of the market. So over 30 years, you might actually solve, you make and actually when you do transmission expansion, this occurs as well. So transmission expansion occurs, and then as you expand, then generators compete to reach an equilibrium, and generators use some understanding of how the market is going to evolve. So you actually have tri-level games that show up. So there are a host of these that show up. Yes, Arnav?
Do you have some references?
On which one of the
The one you just mentioned.
So on the forward market or on the expansion problem?
Yes, there is
Yeah, so in the expansion problem, so On the tri-level version, you can look at the work by, I think, Sarah Ryan. She has Ryan in Iowa has some papers on this, on tri-level. And then Ben Hobbs may have something on this. On the transmission expansion, we are doing something. And I have some references. We have nearly finished. So if you send me a note in a few weeks, we'll have a recent set of references. So we are looking at a setting. So this is with Ben Hobbs, where we're looking at a setting where we have transmission expansion. There's a subsequent game on the generation side. Yeah, so if you send me an email, I'll get you something there. But there are, so I think your first stop should be the work by Sarah Ryan at Iowa State. She's got some papers on that. Yeah, but this is a fairly rich area in terms of looking at hierarchical modeling, and not just here, and it shows up in other settings. So it's a fairly rich set of problems, but I mean, it does suffer from this theoretical shortcoming. It's just, it's unfortunate, but.
Maybe a very basic
No.
question, but when you solve some Stackelberg game where you have like leader problem and follower problem, so I think you have mentioned something about like a bi-level problem when you have upper level and.
It's the same thing, yeah.
Yeah, so then you can use the KKT conditions of the lower level problem and put it in the upper level problem.
Well, that's what we did. That's the MPEC, right?
Yeah.
Okay. That's the MPEC. So the lower level problem, we just replace it by its KKT conditions because they're necessary and sufficient. Okay, so you're left with an MPEC then. And then you solve that MPEC, and that gives you an understanding how the leader would operate and how the follower would respond.
Yeah.
Right?
So, but then, I mean, when you are on this timeline of electricity market, and for example, if it's some forward market and I don't know, day ahead or spot market, so then if you are in the real time, and then you have some expectations of what was happening in the forward market.
So you have to solve this at the forward market level. So remember, since the market that clears first plays the leadership role. So you're sitting in the forward market, you're competing, and you're modeling how the spot market would respond to your forward clearings. So the real time or the spot market would be viewed as the follower, yeah. Okay. So that is the first paper. There is the work by Alas and Leah. Okay, but you have to be a little careful about the claims that I made. At least I'm not, because if it's very simplistic, it just gets hard to. And it was subsequently there have been discussions about that. Yves Smears has some papers on that. There have been lots of people who've looked at those questions. Yes.
It's about the previous. My question is about the previous topic.
Okay.
So if anybody has to.
No, we can keep switching. It's okay. Which one is that? Is that the multi-linear which one? The generalized Nash or which one?
We were
Okay.
discussing it during the break about
Okay.
what happens if we have a situation between multiple regions and there's not there doesn't exist a shared constraint for the whole.
Yeah. So there is. So one of the questions he had was that suppose you have a coupled constraint and but it's not a shared constraint. I mean, it's a network setting, but you can't put a shared constraint for a variety of reasons. Most of them informational, right? You don't have access to that. So I think I don't have a good resolution, because the thing is that problem is a coupled constraint problem. You could add a conjecture where you added the other constraints, but then the equilibrium that you get. So let's put that aside for the time. Suppose you work with a pure generalized Nash, okay, where you just have coupled constraints. One question is that if you made, so you remember that, so there are two questions. One is the question of getting a generalized Nash equilibrium, as in computing one. The second is the question of whether one even exists, right? So the question about whether an equilibrium exists comes down to, so you remember that I'm assuming you have convexity of the upper level. Do you have convex payoffs or cost functions? Okay, so if you had convex cost functions, then if you assume that these The second level problem is just a coupled constraint, but it doesn't come from equilibrium constraints, right? The second level, the coupled constraints they're not equilibrium constraints, right? Or are they're just standard, it's just a standard coupling, but it's...
No, it's an equilibrium problem.
No. The lower level constraints, do they come from another game?
No.
They're just, okay. So they're just some network constraints.
Exactly.
Okay. So I think that your problem looks a bit like this. So I think your problem is this problem, right? Theta I x minus I, xi lies in some ki x minus I, right? Where ki of x minus I, because you have network constraints, I'm going to assume is maybe closed and convex valued. It's a set. So the question is that if you could write this as a QVI, the set valued map K and a mapping F. Do you have capacity constraints in your... So what are the variables here?
Well, it's DCOPF.
DCOPF. So you have basically flow decisions and you have generation decisions. So most of these are bounded, right? So I think that you might be able to... So you remember I had this Harker's result. And Harker's result was that if there exists a gamma such that K of x is less than gamma for all x in gamma, and then f is continuous, then QVI KF has an equilibrium. So I think that you might be able to show existence by directly examining under some capacity bounds whether you can show this kind of result. That for every x, because we know the x is bounded, maybe you can find out what that omega should be. Not omega, that gamma. Okay? So that's one. The second avenue in terms of computation, so the computational avenue, there are two avenues. One avenue is these are convex problems. If you write down the KKT point of this problem, after you write down the explicit conditions, then you can write this whole thing as a complementarity problem. So you could directly try and solve the complementarity problem in path. How large is it? If you write down all the complementarity conditions?
I don't know, I have not derived it yet, but we're talking about like an illustrative example, so it should not be very large.
Yeah.
I
So
will
you,
not calculate.
do you have access to path, the solver?
I will do
Gurobi. So I don't think Gurobi would work on this because once you write down the complementarity conditions, you'll have to use a complementarity solver.
I have to derive the...
Yeah, KKTs, yeah. So once you derive the KKT conditions, you can directly apply path on it, the path solver. That's one idea. The other idea is, there are some algorithms that have been developed for generalized Nash games by Francisco by using I think some sort of penalization methods. I haven't seen it, but he had mentioned some work that he had done. I can't remember. So you can check if they're recent papers. But I wouldn't suggest going there yet because the problem is those methods they've just started. You'll have to develop your own implementation. That's a long-term issue. So I would suggest instead trying path. That's your first stop. Or putting in GAMs and calling path. Okay, I think that's your. But I think existence may be possible, but I'm not sure.
There's going to be multiplicity, right? There's going to be
Yeah, you don't have a uniqueness. It's not even, don't even. So if you get existence, you should go and, light a candle.